Hi everyone, my name is Anthony Nocentino and welcome to my SQL Bits 2020 session, Practical Container Scenarios in Azure. I'm a consultant and trainer and founder of Centino Systems, where I specialize in system architecture and performance. I've been a data platform MVP for the last couple of years and also a friend of Redgate. At the bottom there, you'll find my contact information. If you have any questions about today's session, please feel free to email me or hit me up on Twitter. And I also blog pretty frequently at centinosystems.com/blog. I'm also a Pluralsight author where I specialize in courses on Kubernetes, on Linux systems administration, and also SQL Server on Linux. Now let's dig into what we're going to look at together in today's session. We're going to start off with container fundamentals, where we'll learn what a container is and some of the benefits of using container-based applications. Then we'll work together to create a container image from a .NET Core application together. We'll take that container image and put that into the Azure Container Registry, where we'll learn how container registries work and the value that they provide in our container-based deployments. Then we'll look at how to deploy our application in the Azure Kubernetes service. We'll take our application that we just built, stored in our Azure Container Registry, and then we'll take that and deploy that application in AKS and then scale that application very, very quickly. And we'll also see how easy it is to update an application that is in production. And we'll do that together throughout a series of demos today. Now, let's start off with talking about the benefits of containerizing applications and potentially deploying those in our data centers. The number one reason why we're going to use container-based applications is to reduce development time. The key concept here is to get code from your developers' brains into production as fast as possible, and doing that consistently and easily over time. And that's one of the core ideas behind container-based applications. You'll see how we leverage containers and container registries and Kubernetes to help us take that code and get it from our developers' brains into production in a defined control way. And we'll see that throughout today's session. The key thing here is deployment automation. We want to be able to do things fast, yes, but we also want to be able to do them consistently. We're going to write code to take that code or those container-based applications that we're going to build together and get those applications or those containers into production. Speed and consistency. So we want to be able to do things fast, but also do it the same over and over and over again in code. Now, the next iteration of that or the next development of that is going to be enabling those DevOps scenarios, both continuous integration and continuous deployment, where we can build automation to build those container-based images or container-based applications. And again, get that code, get it compiled, get it into source control, create a container image, and roll that out into prod. And this is how we're able to do that. We're enabling those scenarios with containers and also leveraging techniques like container registries and Kubernetes, or leveraging systems like container registries and Kubernetes. Now, I want you to think about this in a different context. As data professionals, we're kind of used to thinking about things in terms of servers, right? We're going to shift that model when we talk about container-based applications, and we're going to focus on services. Is there a service available for the consumer of that application to consume, right? If I'm a user and I want to hit that application, I'm going to hit the service. Now it's up to something like a container orchestrator like Kubernetes to give me access to the container-based applications. And we're going to see how that all pieces together throughout this demonstration or throughout this presentation today. And so remember, applications, services rather than servers. And we'll see how that pieces together today. Now let's dive into our first piece of tech here and talk about container fundamentals. Containers provide operating system virtualization, where applications will share the kernel and underlying system resources. So think about it this way. I can have multiple containers running on top of a single base OS. Contrast this with virtual machines, where you would have multiple virtual machines sitting on top of some hardware, right? So the level of abstraction is one level higher, where it's going to be inside the OS itself. And that gives us some ability to run multiple applications on top of an individual operating system and kind of relieves us if there's potentially any conflict. So for example, if application A had a library that it needed and application B had a library that it needed, and those two libraries conflicted, well, before containers and virtual machines, we'd have to separate those out onto two servers or even two physical servers. In containers, we can have those separated and isolated and running on top of that shared OS, and those would work perfectly fine together. And so what is a container? Well, a container is your application. It's literally the binaries or the executable code and the libraries that it needs and any file constructs that it needs to run that application itself. And so inside of a container, conventionally you'll see just one application. But there are scenarios where you might have multiple applications inside of one container if there's a real tight coupling there. But conventionally, that's not the case. One app, one container. And the reason is because this becomes the unit of work. When you start up a container, well, what does it mean to start up an application? Do I need one process, two processes? What does that work from? Or how does that piece together in your application architecture? But like I said, conventionally, you're going to see one app, one container. Now, a key concept that I want to bring home is that containers are ephemeral, right? If I start up a container and I delete a container, that container is gone for good. And so that gives us some interesting things that we have to deal with, especially as data professionals, where we have to decouple the configuration and the state from the container itself. We're going to focus a little bit on configuration today, but not so much in state. On my other session at SQL Bits this year, I cover deploying SQL Server inside of Kubernetes, and we focus almost solely on maintaining state of SQL Server and also configuration elements. So if you want to dive into that there, check out my other session, Deploying SQL Server in Kubernetes. But for today's conversation, we're going to see how we can deploy a stateless application and scale it very easily in our Kubernetes cluster. And so let's take a visualization of what a container looks like when we deploy it. And so we can deploy containers on top of physical or virtual machines by installing a host operating system. Now, conventionally, this host OS is going to be Linux, but there are Windows-based containers. Today, we're going to focus on Linux containers. On top of that individual host OS, that's where we'll start up our applications, or our application containers more specifically. So app 1, app 2, app 3, very complex application architecture here. But the idea is that these applications are running on top of that host operating system, and they don't know about each other at all. They can't see each other and interact with each other in any way, unless they needed to talk over the network, and then it would just talk over whatever networking protocols they need to, perhaps TCP/IP. And so app 1, app 2, and app 3 are running on this operating system. They're completely isolated from each other. They could potentially have conflicting libraries, and everything would work perfectly fine. Now, one of the ideas, though, that I do want to drill home is that ephemerality of containers. When it's time to service an application, if I have to patch it, maybe I have to change the deployment model a little bit, whatever I want to do, the idea is that I can just kill that application and deploy that new version somewhere in our data center, right? And you can imagine in this scenario, we could have multiple machines supporting container-based applications, and we'll see how that pieces together later on when we talk about container orchestrators. So now that we know what a container is, let's talk about today we're going to focus more on creating containers. Well, a container, as we introduced a second ago, is made of an image. And just to kind of nail down the actual terminology, a container is a running image. An image is your actual program code, runtimes, libraries, or whatever you need to run that application. And you can also include environment variables, which allow you to be able to specify or decouple configuration from inside the container image itself. Now, with the container image, we use registries to exchange those images. So effectively, a container registry is where images live. And so you might have heard of Docker Hub or Azure Container Registry, but you can also have an internal container registry on-prem if needed. Today, we're going to focus on Azure Container Registry, and we're going to build a container together and store it in Azure Container Registry and then pull it down and run it inside of a Kubernetes cluster. A Docker file defines the container image, basically what goes into the container image, how to start it up, and potentially does it list it on the application port or maybe even mount some sort of persistent storage external to the container itself. So to create an image, we'll write a Docker file, and we'll look at the syntax of that in a second. In that Docker file, we're going to define what application we want to run and potentially any binaries or libraries that are associated with that application. We'll run a process called a build or a Docker build in our scenario today, which will then create a binary image that has that configuration of the container and also those needed files, takes those, makes a single binary image, and pushes that into a container registry. So the first part is a Docker build, creates the image. That's going to be stored locally on your machine. And then you push that image into a container registry. Now, when you're ready to run that application, you do what's called a pull, right? You might have seen Docker pull. Now, Docker pull is going to then you're going to run that command on a host OS, which will then pull that image down from the container registry, read its configuration, start up the application, and potentially expose that on a network port on your local host OS for users to access. And so the key idea here is you can kind of see the workflow, right? We're going to take our application, we're going to build it, push it into a registry, pull it down to run it in our application. And so now let's look a little closer at Docker files together. A Docker file describes the commands to build an image. And so if I want to build this image, that I'm going to deploy some sort of application. In our scenario today, it's going to be a .NET Core application. Well, we need to tell Docker what it needs to run our application. And commonly when you're working with a Docker image, you're going to build off of someone else's work. And so if I'm building a .NET Core application or whatever application it is, chances are I can consume some prepackaged container image and then layer my application on top of that. And so here we see some code that would go inside of a Docker file. We're saying from mcr.microsoft.com, .NET Core ASP.NET 3.1. And what we're saying here is I want to be able to take that image and download that image, which is going to be the things that I need to be able to run ASP.NET Core applications. Now that container image is going to be serviced by Microsoft. So I know that I'm getting that from the actual publisher or builder of ASP.NET Core, right? That's pretty much as good as it gets when it comes to consuming an image and getting it from a trusted source. Now, there are some integrity and trust issues that go into building off of other images. That's kind of out of scope for today, but you really want to be able to use the images that are being provided from the actual vendors themselves or build your own. So now the next part is your application, right? We're going to take that ASP.NET container and we're going to build on top of that. And we're going to copy an application. So here we see I'm going to copy my web app and then the compiled binaries associated with that are published in this /publish directory. And I'm going to copy that into a directory inside of the container app. And then we'll define next how we start that application, right? Because we're telling the container what it needs to do. So we define an entry point. We're going to say, you know what, launch the .NET executable and call this DLL in the directory app, which is mywebapp.dll. Now all that together gets us a running application, but I need to expose it so that users can access this application over the network. And so this really is kind of the bare bones Docker file that you would need to create a container-based application. We're going to build off of the ASP.NET Core image. We're going to copy our application in. We're going to define what needs to be started and then expose it inside of our container. Then we're going to take that and we're going to save that into a file that is going to be the Docker file, which we'll conventionally call Docker file. And then we'll do the process of building the container image. So we'll say Docker build -t tag, and it will define a tag name, which in this case is going to be my web app image. Then we'll use a space and a period there at the end to say, you know what, read the Docker file that's in the current working directory. And then it will go through the process of executing these steps to pull that ASP.NET Core image, copy my files in, and then build the binary image with that is associated with the Docker file, and then we'll have a container. Now, not gonna lie, Docker build's a pretty complex process and a complex system, but it gives you lots and lots of room for configuration. So I encourage you to read the reference documentation about building containers, because that's going to be, for handcrafting these things towards your applications. Today, we're going to focus on just getting the bare bones container up and running. Now, when we execute that Docker build, it's going to generate that container image on our local system. And what we want to do is be able to share that container image either with other people or other systems like Kubernetes. And that's where container registries come in. Container registries store container images. And that gives us a way to really freely exchange these container images, whether it be internal or external to our platforms. And so we can build both public container images, which you might be used to with consuming images from maybe Docker Hub or the Microsoft Container Registry, or you can also build your own private registries, either on-prem that are completely off of the internet or on the internet and that require authentication. Now, in addition to public and private registries, the actual container image itself is secured in a couple of ways, in that the transports exchange, like when I'm bringing or pulling down a container image onto a local system, that's going to be encrypted over HTTPS. But more importantly, or I shouldn't say more importantly, but very importantly, is the content is secured. And this is a key concept to really focus on inside of container images, that you want to make sure that what you're pulling down from a container registry is what the person who built the container and published it onto the container registry put there. You really want to make sure that that hasn't changed. And that's done by a series of digest or hashes on the container image's manifest or its definition, and then also the image layers that it's comprised of. And so very important there, knowing that what was published is what you're consuming. And you'll see container registry images digest. As we start going through today's session, you'll see these hashes pop up periodically when we start looking at the containers and things like that. So a very important concept there is that they're secured for the content that is exchanged. Now, container registries become a key component of building CI/CD pipelines, right? You can kind of see that workflow that we had when I introduced how a container was built. And then if you layer automation on top of that, so as code changes, well, then a container will get built, it'll get pushed and potentially pulled and roll out in production. And so that's that CI/CD pipeline scenario that you've heard so much about that enables DevOps to be able to get code from developers' brains into production as quickly as possible. Now, when you're looking at container registries, images are going to be organized by tags. And so you'll see today we're going to build our My Web App image. We'll build a V1 and a V2, and I'll adjust the tags associated with the container images based on the versions of the applications. Now, the tags are arbitrary strings that I think of to apply to, but they provide some meaning to the consumer. So you know V1, V2, or if you've worked with the SQL Server image, you'll see they'll kind of encode what that image really looks like. You'll see SQL 2019, CU5 on Ubuntu 18.04, and the tag will be built to represent that. You'll also see the latest tag, which conventionally will point to the newest version of an application. Again, that's a convention of how container registries work, not necessarily the absolute law of what's out there. And we've already discussed a little bit that kind of the main place for exchanging and consuming registries or container images on the internet is Docker Hub, especially if you're in a Docker universe. And there's also the Azure Container Registry, which we're going to dive deep into here momentarily. When you're working with Microsoft, you'll see lots of their images are going to be on mcr.microsoft.com, Microsoft Container Registry. And so if you're working with things like PowerShell or ASP.NET or even SQL Server, those assets are stored inside of mcr.microsoft.com. And so up next, let's get into our first series of demos where we're going to create a container-based application together. We're going to take a .NET Core web application and build it as a container locally on my laptop here. And then we'll learn how we can build container images directly inside of Azure Container Registry. So we talked about the concepts of pushing an image into ACR. Well, ACR gives me the ability to throw my code and a Docker file at it and push off that build task into ACR and store that image locally. We'll talk about the benefits of that when we get into the demo. All right, so here we are logged into VS Code, and let's walk through the demonstration of creating a .NET Core web application together. On my system, what I have installed is I have Docker, .NET Core, and Azure CLI. Those would be the components required to reproduce this demo. Now, I'm not a developer, at least I'm not anymore. I spent a couple years writing code for a living, but what we're going to do here is just build a simple Hello World-like application in our container image here today. And to do that, we're going to basically use this .NET application to restore a vanilla C# web application. So we can do that with .NET new web app and then specify a directory for a directory for output with the -o parameter of my web app. If I take a look inside of the directory my web app, we see kind of the core elements of a C# based web application that we're going to work with today. Now I've customized an HTML page that we're going to work with, so let's copy that inside of there, and we're going to see how we can build this complex web application together. Let's go ahead and change into that directory, compile and run that application with the .NET run command. That's going to run this application locally on my system and give us the ability to test out this app to make sure that it works, right? Before we even get close to building a container image, we want to test out, does the application do what we think it actually needs to do? So let's go ahead and background that process and run this command. Our application is going to listen on localhost port 5000 by default. And so I'm going to pop open a web browser here. And inside of there, we'll see the application very, very simple. It prints out my host name, which is MacBook Pro, and tells me the version that we're working with. So here I just specified, you know what, this is 1.0 of our very basic application. So now that we know our application works, let's make a container. Let's go ahead and bring this into the back or bring this into the foreground and break out of there with Control C. We're going to .NET publish a release. So basically compile and build a release version of our app. That's going to get us that core DLL that we'll use to run inside of our container. Let's go ahead and change back into the parent directory here and build a container image. So the first part of the demo, again, just building an app, making sure it works, right? And we did that. We saw that we have our application up and running without any container technology there, just basic web app. Let's go ahead and build a container. We're going to specify inside this Docker file what we want our container to look like. We're going to build off of that ASP.NET Core image, which is going to have the tag version 3.1 because we want to use that specific version of ASP.NET Core. Now we're going to copy that library that we just built together into the app directory, and then we'll define the entry point for the container is the .NET executable with the parameter of the DLL that we just created, and then expose that on port 80. That's where we'll point users to consume this particular application if we publish it on that port. Or more precisely, that's where we will route traffic to inside the container. We're going to publish it externally on our base OS on a different port, and we'll cover that momentarily. So inside that Docker file, we just specify where it's coming from, like we're building on top of that image, what we want to copy in our application, how the program starts, and where the container is listening on the application port. Now let's do the build process. So we do Docker build, we specify -t for tag, my web app, version 1, right? So that's the convention. Image name, my web app image with a tag of version 1. So that's just something for us to know that it's v1 of our app. And we're going to point it at the working directory to read in the current working Docker file. Run that command there, and it's going to go through those steps to create the container image. And so now locally on this OS, or my local system here, I'll have a container image that is my web app image, which we can see here on this line right there. See my web app image. So let's go ahead and run a container from that image that we just built together. And we can do that with the command docker run, specify a name for the container. Now this is where we'll publish the port itself. So inside the container, we're listening on port 80. Outside the container, we're going to send users to port 8080. So that's where I would send traffic to access this particular container image. Now, why would you do that? Well, potentially I could run more than one web application on port 80, but I wouldn't have to customize that inside the container. That's a runtime decision that I make when I deploy on what port I want it to listen to. And then I can juggle who's listening on what, potentially on systems if they're co-resident on the same system and have a port conflict. We then specify the container image that we want to run. So we see my web app image v1. Let's go ahead and start our container-based application up. If I do a Docker PS, I can see that my container is using, it has this ID right here. It's going to be using our image. There's the command that it started up. We can see .NET, and then there's our DLL. It's abbreviated with some ellipsis. We can see that we're listening on all IPs on port 8080, and we're sending our traffic to the container port that's exposed inside of our application on port 80. And so now if I go and access localhost 8080, remember this container is running on my system on port 8080, right here. If I run this code to access that, I'm going to jump over to a web browser. I got a little bit of a mess up with the layout, but the core elements are there. We see the host name, right? So there we see the actual name of the container ID ending in 4BB. And then we also see the application version v1. So before, when we ran it on localhost 5000, it was running on my local host on my base OS, right? And so it was just a process running on the base OS that anybody could see. But now it's running inside of a container and it's isolated. So it thinks it has access to that underlying OS completely by itself. And it also thinks that underlying OS's name is the container ID, right? Ending in 4BB. And if we jump back over here, we can see it ends in 4BB. And so that's one of the core concepts behind the isolation of containers is the running application thinks it has access to the base OS all by itself. Now, for the next part of this demo, let's go ahead and build that container image, but this time we're going to build it directly inside of Azure Container Registry. So I've already gone ahead and logged into my Azure account, but here you can see I have the Azure CLI code to do that. I've created a resource group in Azure already called Practical Container Scenarios in Azure. And so you can reuse this code to reproduce these demos if needed, just adjust the parameters for your situation or your account. Now, what we have here now on line 74 is the command azacr create, which creates an Azure Container Registry inside of Azure for us. And that's where we're going to put our container image here momentarily. I've already gone ahead and created that. And if I use the Azure or the AZACR show command and specify the name, let's see if we get that right. I bet you I didn't specify. Oh, no, I did. There we see that, just to make sure that our container registry is up and running. And here we can see we have our container registry up and running. If we want to, we can check this out in the portal by clicking on this link here. So let's do a command click, jump open into the portal. And inside of there, you can see our container registry is up and running. And I've also pre-configured our AKS cluster for later on in this demonstration. Now, one of the key things I want to call out here, and it's different than we just did with the Docker build, is we're going to use the AZ command, AZACR build, and we're going to specify the container image that we want to name it. This will be the name it inside of our Azure Container Registry. And again, it's going to be my web app image v1. The registry is going to be the ACR container registry that we just built together, or the one that I pre-built before this demonstration. Now this dot here is going to read the Docker file in the current working directory. So this one right there. Now when I execute this command, rather than building the image locally, what it's going to do is ship that Docker file into Azure and also zip up all of my code locally and ship that into Azure. And then it's going to build the image inside of ACR. And you might think, well, why would I want to do it that way? Well, that way I don't have to transport the whole container image. I'm just shipping my code and a Docker file. And so now on the screen here, you can see what ACR did is it kicks off the build inside of Azure. So those elements are happening inside of the Azure Container Registry for us. Once that build's done, it'll be stored inside of ACR for us to consume. The savings there is we didn't have to transmit the entire image. Yeah, and so in the output at the bottom, we can see successfully tagged image, and that's going to be built and stored inside of our container registry. Now it's being built on a host inside of Azure, and then it will then be pushed into our individual container registry itself. And so at the bottom here, we can see it took about 41 seconds for it to complete that process, and that the image is available in our registry at the repository named my web app image with the tag v1. And here you can also see an example of a full image digest right there, which is a SHA-256 hash of the image's layers and also its manifests. So let's jump back into the presentation now and look at the next part of our session. All right, so now that we have containers, let's talk about how we deploy containers in systems. And so if I need to build a complex, potentially microservices application, or even just a regular, or even just a distributed system, I should say, well, how do I do that with containers? Do I go up to servers and type Docker run in my data center? No, not really. And so we have some questions that we have to ask when we talk about modern application deployment. First up is, where do I run the app? Like, where do I run these container-based applications in a collection of resources in my data center? How do I scale these applications? Again, do I want to run up to servers and type Docker run over and over and over again? How do I consistently deploy a potentially complicated application that's made up of multiple containers? And then how do I access this app? How do I get users to access the front-end web applications? How do I get them, maybe the web applications to hit the caching tier, and then the caching tier to hit the data tier? How do I piece all of that together? That's where container orchestrators come in. A container orchestrator has some core jobs. We're going to talk about those right now. And first on that list is workload placement. So again, rather than running up to servers and typing Docker run, it's the job of a container orchestrator to figure out within a collection of resources in a data center where to run application containers. Now, moreover, in addition to workload placement, container orchestrators also have the function of managing state. So if I say run 2 web applications, a caching tier, and a data tier, it's the job of the container orchestrator, well, to start those containers up somewhere in my data center, and also to keep those up. Perhaps if a node dies that's supporting a particular container-based application, well, do I want the container orchestrator to start up that container somewhere else in the data center? Probably, and container orchestrators provide that by managing state. Container orchestrators also provide networking and services. We'll look at a little bit, or actually we'll look at in pretty good detail what a service is and how that gets us access into our clusters to access our container-based applications. Container orchestrators also provide some rudimentary load balancing services and can also integrate with more advanced load balancing services either in the cloud or on-prem. And we'll see some examples of that in our demonstrations today. Orchestrators also provide persistent storage. So if you have a stateful application like SQL Server that needs access to persistent storage somewhere in your cluster, well, then that's a key concept inside of orchestration. And again, we covered that in great detail in my SQL Bits session, deploying SQL Server in Kubernetes. Now, another key element of orchestration is a declarative model. We're not going to tell our container orchestrator exactly what to do. What we're going to do is we're going to write code that describes what we want it to do. So for example, start 2 web containers, start one caching tier or one caching tier container, and start one data tier container and attach some storage to that, and then expose those web applications on a public IP address for users to access. And we're going to write code that describes what we want rather than actually configuring those elements in our cloud infrastructure. And we're going to see how that pieces together when we look at a deployment here in a few minutes. Now, some of the key container orchestrators that are available out there, well, you'll see Docker Swarm and maybe Docker Enterprise, but this is the one that you're going to see the most, is Kubernetes. Now, Kubernetes is an open source project that came out of Google and is an open source platform. And so some organizations require that you might need to use a distribution that is managed and supported by an organization. And that's where things like Red Hat OpenShift come in. So OpenShift is basically Kubernetes, but for sale from Red Hat so that you can have support contracts and things like that if that's required for your industry. Now, in addition to OpenShift and Kubernetes on-prem, we have managed services in the cloud. So we have Azure Kubernetes Service, which we're going to focus on today. We also have GKE and EKS and many other variants of this, but these are the core services from each of the cloud providers that you might be familiar with. Now, let's look a little more closely at a Kubernetes cluster itself. A cluster really is a way for me to aggregate compute resources or resources in my data center for me to be able to deploy applications into. And Kubernetes gives us the ability to write code to describe our systems. We feed that code into our cluster, and it's the job of Kubernetes to affect that desired state and get us into the state that we describe in our application code. So if I want to deploy the complex application that we looked at a second ago, I write the code that describes it, I give it to Kubernetes to deploy, and Kubernetes figures out where to run those applications inside of my cluster, or those container-based applications inside of my cluster. If I need storage attached to my data tier, that's attached. If I need a public IP address for users to hit the web front ends, that's exposed, and users are able to hit these applications. And so that's kind of the core philosophy behind what the core value behind what a Kubernetes cluster provides to you. Now, we're going to focus on AKS today, or Azure Kubernetes Service. AKS is a managed service, so we can just say, you know what, I need a Kubernetes cluster and I just want to consume that from Azure. Now, you can go get a bunch of virtual machines or physical machines and deploy Kubernetes on top of that. In fact, I have a whole series of Pluralsight courses dedicated to hand building these things. But from day-to-day operations for me and for customers that I work with, we use AKS to do, I do this for my demonstrations when I'm just kind of knocking around, wanting to play with things, and also for customer scenarios where we deploy applications inside of Azure Kubernetes Service. So AKS is a managed cluster. And what that means is things like upgrades are going to be managed for you. So moving between versions of Kubernetes is as easy as either running some Azure CLI or making a change inside of the Azure portal. When you deploy a Kubernetes cluster, you're going to define a number of nodes that you want. And today, we're going to get 3 nodes when we deploy our cluster, but we can get 3, 30, 50, however many nodes that we need to run our workload. How many nodes do you need? Well, that depends on the number of resources that you need to run the applications that you deploy. And so to kind of bring it back to maybe something that you're familiar with, when you built virtual machine-based clusters, you spec'd how much CPU and how much RAM that you needed to run all of your applications, and you built in some overhead for redundancy. Some of the key concepts of those same concepts apply here. Now I have the word agents in parentheses here. You'll see in some of the Azure documentation and on the portal that nodes are referred to as agents sometimes, but in Kubernetes terms, those are nodes. Nodes are going to be deployed in availability sets, so you get the redundancy there, and they're also deployed in what are called node pools, so you can kind of commingle potentially different sized virtual machines inside of Azure. I just let the secret out there. Behind the scenes, the AKS cluster is built of virtual machines, but the good news is you don't have to get into the business of maintaining and managing those VMs. AKS handles that for you. And the node pool is an abstraction around that, whether it be on versions of Kubernetes or on types of virtual machines, specifically the types of VMs inside of Azure, whether it be the different SKUs for different capacities, such as CPU, disk, and RAM. And so now that we know roughly what Kubernetes is, a container orchestrator, and what a Kubernetes cluster is, resources in our data center, and specifically today we're going to work with AKS, which is a cluster inside of Azure. I want to talk real briefly about how we get Kubernetes to do those things. How do we write the code to describe what we want done? And that's where the Kubernetes API comes in. The Kubernetes API services a collection of objects that represent the resources that you want to deploy in your system. And so that's really kind of the API to access our cluster and affect the desired state that we want upon that cluster. And so we're going to write code that describes what we want it to do. Now we have additional API objects that describe the core elements of the systems that we want to build. And so the first one that we're going to talk about today is pods. Pods is an abstraction around your container-based application. And so that container that we built earlier, well, we're going to deploy that as a pod in our cluster. But we don't get in the business of creating pods individually inside of our cluster. We don't say create 5 pods. What we'll do is we'll define a controller that describes that desired state. And so in a second, we're going to talk about a deployment. And so what we'll say in that deployment is we'll say, you know what, I want some number of this container image running up. Maybe it's 5, maybe it's 10, maybe it's 50 of this particular container image up and running at all time. And it's the job of a controller to maintain that desired state. And specifically, the deployment controller is the one that we're going to look at today. Now, services are a way that we can provide persistent access to our application. And so we'll describe a service that will then deploy a load balancer and give me a public IP address to access our container-based applications that we deploy inside of Azure. And services can come from many different types. We're going to focus on the Azure load balancer, the load balancer type service inside of Azure today. We also can have storage for persistent storage for our applications. We're not covering storage so much in this session. We're covering it in much more detail in my other session on deploying SQL Server in Kubernetes. But these API objects, pods, controllers, services, and storage are really kind of the 4 core building blocks to deploying containers or container-based applications inside of Kubernetes. Pods are our apps, controllers describe how we want them deployed and the number that we want them deployed, and services provide access, and if we need storage, we can provide persistent storage. Those are the core ones. There's many more because you're going to be able to build more complex systems and constructs and security boundaries, and all those different elements are exposed to us via the Kubernetes API. But like I said, today we're focusing on these core elements. And so let's look a little closer at services and another API object or a controller that is a replica set. We'll see how replica sets work. And then in a second, we'll see how they work together with deployments to roll out applications. And so in our cluster, when we describe a deployment, that deployment creates a replica set. That replica set is what has the responsibility of creating the pods somewhere in our cluster, right? Those pods will get started up and scheduled onto physical nodes in our cluster. We then describe a service to get access to the application that we want to deploy. So the application service, the service itself will get, in this case, a public IP address and be exposed on a specific port. We're working with a web app today, so that port will be port 80 or 8080, whatever it is that we want it to work with. Then we'll point users at that service, right? So traffic will get sent into the persistent and potentially public IP that's allocated for the service. The service will then load balance that traffic onto the pods inside of that replica set. And that workload will get distributed via the Azure load balancing service. Now, in our AKS scenario, now let's say something like this happens. Maybe one of our pods crashes, or the node that pod is running on just dies and disappears. Well, the replica set is a controller that has the responsibility of affecting the desired state on our cluster. And we told Kubernetes to create a deployment of 4 copies of this particular application. And if that app dies, it's like, well, there's only 3 copies left. And the replica set that's part of that deployment will do this. It'll kill that pod and then create that pod somewhere else in the cluster. And what's going to happen behind the scenes is that pod that failed is going to get deregistered from the load balancer, and that new pod's going to get registered into the load balancer, and traffic will start getting distributed to that new pod in our cluster. And we just had a very, very short period of diminished capacity before we get back into that desired state. And this is a fantastic piece of functionality that I really, really appreciate in the production systems that I support. Now let's zoom out a little bit. No one really gets in the business of creating replica sets directly. We're going to create an API object called a deployment, and that deployment creates the replica sets for you. I'm going to show you why that's important right now. That deployment gives you an abstraction around replica sets, and so we can declaratively move between versions of replica sets. And let's see that in action. So I create a deployment and I describe the number of replicas that I want to have running and the container image that I want to run, amongst some other configuration. What Kubernetes will do when we create that deployment and give it to the API server to run is it'll create that replica set and then go pull those container images and start those pods up somewhere in our cluster. Now, in addition to the deployment, we'll expose access to these applications via a service. Again, maybe it's HTTP, and we point users at that persistent IP to access that application. Now, this is where deployments really shine. We'll see why we don't use replica sets directly, but we'll use deployments to move between versions of replica sets. So if I get a new version of my app, let's say our Hello World application v2 comes out, right? And we push that into our container image, or into our container registry. Well, we'll update the deployment by changing the tag specified in the deployment, right? So inside the code that describes this thing, we said run v1, and I'll change that to v2. When we do that, we push that code into our cluster, this is what happens. What Kubernetes will do is create a new replica set. It'll then start up pods running on the new version of that application. So here we see v2 is up and running, and it's shut down one of the v1 pods. It'll then shut down the remaining v1 pods and start up the remaining v2 pods. And what we had there is potentially a zero downtime rollout if our application can support that by just changing the tag in the deployment manifest that describes the deployment that we want deployed. While it's making that transition as pods are shut down and pods are started, the old pods are getting deregistered from the load balancer and the new pods are getting registered into the load balancer, again, affecting that change with zero downtime. Now, what you'll also see here is I didn't delete the old replica set. That old replica set is still available to me, and that metadata about that API object is still stored inside the cluster for up to 10 iterations by default. And so what that means is I can roll back, right? If something went wrong with v2, I can run one command and roll back to the previous version of that application. So now let's look at how we actually deploy applications into our cluster. We covered the theory about how the objects and controllers work together to deploy apps. Let's look at how we can actually affect that change in our cluster. And the first technique that we're going to discuss is imperative techniques. We can certainly walk up to our cluster and execute a command like this that says, you know what, kubectl, which is the command line way that we're going to interact with our cluster, kubectl create a deployment named web app and use this image that we have stored in our Azure container registry. And that'll go and that'll pull the container image. It'll start it up in our cluster. It'll create a deployment associated with that. And we can execute another command to get a service exposed to get access to that deployment. But what we don't have here is any configuration artifacts that describe what we did. We just have a series of commands that we execute in our cluster. What we want to head towards is using a declarative code to define our desired state in code. And what you'll do is we'll write manifests in either YAML or JSON that are literally the definitions in the API objects that we want to deploy in our cluster. We take that code, park it in source control, and that's going to describe the state of our system, and we can track that over time. That's also going to become a core element of CI/CD scenarios where these configuration artifacts are generated for you dynamically and deployed into the cluster for you programmatically, again, declaratively. Now, if we did do this in files, which we're going to use today rather than pipelines, we use the command kubectl again, and we'd apply perhaps -f, the read from a file named deployment.yaml. Inside that file will be the YAML that describes what we want deployed. In this specific scenario, we're going to deploy a deployment, and we'll walk through that code together in our upcoming demo. And so now it's time to get into that. Let's go ahead and get into some demos where we're going to declaratively deploy some applications inside of AKS. We're going to look at deployments specifically and services. And then we're going to take our application that we deployed in ACR and deployed inside of AKS and scale it from 1 to 50 replicas in one line of code. A fantastic piece of functionality there that I love demonstrating. All right, so here we are back in VS Code. And on line 94 here, I have the beginnings of the code that describes how to deploy an AKS cluster inside of Azure. And here you can see I'm loading up an environment variable that describes the name of the cluster that I want. And I'm also using this command AZ get versions to get the version of Kubernetes that I want to deploy. Versions inside of Kubernetes is going to be a thing where you need to, I guess I can say this most accurately, it changes very, very quickly. And you want to be able to work with the version that's compatible with how you want to deploy your applications. And I don't want to dive too far into that, but basically what I'm doing right here with this code is getting the latest version of Kubernetes deployed in my AKS cluster. Now on line 105 here, I have a series of commands that will create our Kubernetes cluster for us. And so we have AZ create, our resource group name. We're going to give it a name and a location, specifying the version, and also the parameter generate SSH key, which is required when you create it with Azure CLI. Just to make sure that everything's up and running, let's do an AZ show against our resource group and name. And at the bottom here, we can see we have the JSON description of our object. There we see our first agent pool. We can see count 3. There are 3 nodes in our cluster. That's a node pool, which is a collection of VMs or nodes that are part of our cluster. Going down a little bit further, we can see that the OS type is Linux and that the provisioning state is succeeded. So let's go ahead and break out of here and get back into our deployment. Now, the next 3 steps, which I've already executed, and again, I also executed that, I just showed you the AKS cluster. But anyway, the next 3 lines of code here give our AKS cluster the rights to pull images from the container registry that we built in the last series of demos. I ran that code ahead of time and made sure everything works. But basically what we're saying here is get the client ID for the cluster, get the ID of our container registry, and allow them to talk to each other, or more specifically, allow Kubernetes to pull images, which we want to be able to pull the image that we just stored. If you don't have kubectl installed, which is the command line way for us to interact with Kubernetes, you can use AZ install CLI to do that. The next thing that you'll need to do is make sure that you have the ability to log into your cluster via kubectl with a credential, and that credential is available to you via this command here. So AZ get credentials, and that's going to pull the credential down and store it on your local system so that you can interact with the cluster using the command line. And so on my Mac here, I have kubectl installed. And if I use kubectl cluster info, I should be pointing at our AKS cluster. And here we can see the name right there, AKS Practical Container Scenarios in Azure. And that's the location of our Kubernetes cluster, or more specifically, the API server itself. If I do kubectl get nodes, we see the nodes behind my cluster. So there are the 3 nodes running version 1.18. And so let's go ahead and deploy our service and our deployment. I'm going to run this code here together. And so there we see that our service went unchanged, which I previously deployed because it takes a second for load balancers to get provisioned with their public IPs, and that our deployment was created. So while that's going, let's look at those 2 YAML files that describe our deployments and what we just rolled out. So this is the code that describes what we want Kubernetes to do inside of YAML. And so we have an API version, which describes the version of the API that we're coding against, kind of like the specific version of an API for objects versus the system software of Kubernetes itself. We also have the kind, which is deployment, which we're going to create a deployment object. We're going to give it a name, web deployment. Now inside the spec here is where we describe what we want to have happen. So for this first part of this demonstration, I'm going to say, you know what, just run 1 copy of my container-based application. Now inside the template here is where we define the details for the specific container that we want to run. So here we see the name, or here we see containers, the name of the container, and then the image itself that we want launched inside of this deployment. And that's the path to my container registry inside of ACR. And there's our my web app image that we created together, version v1. And this is the container port, or the port that was described inside of our Docker file with the expose command on port 80. And so that's what the application itself is listening on inside of that particular container inside our pod. Now in the service YAML, we describe the service and the port that we want to send traffic to. So inside the spec, We have ports, and then the port specifically listens on port 80. You can have multi-port services. That's why this is plural here, and the ability to describe multiple ports inside an app. So port 80 on TCP, and then this is the port inside the container that we just looked at in the deployment. So traffic will be received on port 80 and routed into the cluster on port 80. If I wanted to change this to perhaps 8080 or even some other arbitrary port, I could do that here. The type is going to be load balancer, which in Azure will provision an Azure load balancer for us. And so if I do a kubectl get deployments now, we'll see that our application web deployment has one pod that is up and running and ready and available. Here we'll see the replica set that supports that deployment. That replica set has the responsibility of starting out the pod. And if I do a kubectl get pods, there we can see our running application up in the cluster. And so let's check to see what our service IP is. So there we see literally the public IP associated with the service on 52.154.48.239. So let's grab that service IP and store that in an environment variable and use curl, the command line web browser, to access our service. And here we see I do a curl -s specifying the URL location, and I'm doing grep on system, and we get system host name, web app deployment, which is the pod name itself, ending in ZQVLZ. If we looked up a little bit higher, we saw the pod name itself is running right there. So the container is up and running, it's isolated. It thinks it has full access to the host itself. The name of the pod here is inside of our application. If I go and try to access that app here on the public IP address, so 52.154.48.239, there we see the system host name, web app deployment on V1, right? So that's up and running inside of AKS. So think about what we just did there. Compiled some code on our laptops, put it into ACR, and deployed it in Kubernetes in less than 30 or 40 minutes, as long as we've been talking in this session. So let's take that app and scale it. And we're going to do this imperatively now. I could go and deploy another YAML file by just updating this line from 1 to 10 here, just right here if I want to 10, and push that back into the API server. It would scale that execute that scaling operation and deploy 10 pods. But we're going to do this at the command line here, just so you can see it from a different angle using imperative commands. And so there we see our deployment was scaled. Let's check out the number of pods that are up and running. If you think about what I just did there, I just said, run 10 more of these things. And within 7 seconds, I got 10 of those things, or 9 more of those things, up and running that fast. If this was virtual machines, that would take a very long time to be able to provision 10 VMs to support an application. Now, in addition to that, as those pods got rolled out, the load balancer was updated and workloads already being distributed to those, which is, again, a fantastic piece of functionality. Maybe I want to get a little crazier and deploy 50 replicas. So I can then scale that from 10 to 50, again, with one line of code. If I do a kubectl get pods now, I already have 50 pods up and running. Again, a crazy amount of functionality when you consider what we just did there by scaling our application out to support 50 independent application instances running as pods in containers in our AKS cluster, and also updating the load balancing service to do that. Now, if I go ahead and run this command over and over again, you'll see I'm hitting the web server or web service over and over and over again, and it's getting load balanced to all the different pods that are up and running in our cluster. Right, so that metadata that's associated with the load balancer already knows about these 50 pods and is distributing that workload. Now, we do need to make sure that we have the appropriate system resources to support that scaling. I just can't stand up 500 pods or something and not have the appropriate CPU and RAM to support that workload. Now, let's do one more thing. Let's update that container image together. So I'm going to go through this pretty quickly, but I'm going to walk you through the process. I'm going to update our landing page in our C# application. I'm going to go ahead and change into that directory. I'm going to then build a new version of my app. Let's go ahead and back out of that directory and push that into ACR to build. So basically the same process that we did in the last demonstration, but this time I had to change some code, and I packaged that code up, shipped it into ACR with the Docker file, which is then going to emit a new container and store that inside of ACR with the tag v2, right? So you can see where we're going here is we're basically going to update that code and push it into ACR and then roll that out into Kubernetes. I'm going to show you how quick and easy this is to do. So now that that build's done, if I go over to deployment v2, this one has 50 replicas up and running again. Most of this code is identical to what we just had, but the key difference here is whereas before we had v1, now I'm pointing to v2. And so let's go ahead and roll this code out. kubectl apply -f, deployment v2.yaml --record. And now what it's doing is it's going through that process of starting up new pods on the new version of the container image and shutting down pods that were on the old container image and gracefully managing the transition between the two and updating the load balancer to distribute that workload to the new pods and deregister from the old pods. And so this is going to wrap up here in a second, and we're going to go ahead and test out access to our application. So if I open up a web browser to our service IP on port 80, jump over to here, and I'm on v2 already, right? So think about what we did there. In a matter of a minute or two, I built a new app, pushed it into ACR, and deployed it inside of Kubernetes. And that's really kind of the core concepts behind CI/CD pipelines, but with automation, right? We wouldn't be doing that by hand. We would have code that drives that change for us. All right, so let's head back into the presentation and kind of wrap things up. So in our demos, we went through a lot. We deployed an application inside of AKS. We looked at deployments and services, and we scaled our application from 1 to 50 replicas. And we also rolled out a new version of our app. Again, this is crazy functionality if you're coming from the universe of building applications and deploying them on servers or virtual machines. And so where do we go from here? Like, what do we need to learn to really start doing this inside of production? Well, of course, data, right? We need a data tier of some database service and be able to build those connections into that data tier and affect that configuration inside of our applications. We also need to build a production ready application tier. Like what we did today was just demonstration to kind of describe the functionality, but things like connection strings that would be stored in Azure Key Vault. We'd use things like SSL termination and App Gateway. You can integrate App Gateway as your load balancer or what's called your ingress controller inside of your cluster, or even just using other types of ingresses in your cluster as well. And then again, extending what we did manually into DevOps scenarios where you automatically build container images and then deploy that into your cluster with configuration elements or artifacts that come out of your build pipelines to roll that out into production. And so you'll see things here like Azure DevOps or even in GitHub where you can build these pipelines for yourself automatically. Now to wrap things up, we covered a whole bunch of material today. We looked at what a container is and how to build a container image. We looked at how to leverage ACR to store our container image to be shared over the internet, right? We took that code from our local system, pushed it into ACR, and built an image, and then another Kubernetes cluster that was just a cluster on the internet accessed our ACR service to pull down that information or to pull down that container image to deploy our application. And then we deployed that in AKS and scaled it and updated it and did all of that fun stuff. Now, if you want to get started with Kubernetes, that's, obviously I'm a big fan of AKS and hopefully you'll work with it after today. But if you have Docker for Windows or Docker for Mac installed, you have Kubernetes on your local laptop today. Inside the preferences for Docker, you can check a checkbox and deploy a Kubernetes cluster on your local laptop. If you have access to any of the major cloud providers, like we said today, AKS is kind of my way to go. And here's a link to a way to get access to, a link to a startup document inside of AKS. Now, like I said earlier, I'm a Pluralsight author. If you want to dive into Kubernetes for 20 or 30 hours of content, please click on that link there and you can get into those gory details there. If you want access to those courses for free, send me an email. My email is right here on the middle of this page, and I can get you a 30-day free trial access code to my courses on Kubernetes if you want to dive into more details about that. The code for today's presentation is available on that GitHub link there. And I appreciate you all watching and coming to SQL Bits 2020 virtually. So thank you so much for joining me. There's my contact information, and I hope you enjoy the rest of the conference.